I've been on, I've done a Christmas lectures, and we've always delivered it to your year group. This year is no different, although I think this year we've excelled. We've gone beyond what we usually do, and I think you'll be very impressed with what we do, I hope. Before we go any further, I just want to give you a little bit of the history of what is a Christmas lecture and where it comes from. I think that's important. So, Christmas lectures are something that the Royal Institute, that was the main centre for science in England, started to do. And the first one ever done was done in 1827. Now, it wasn't this guy. This guy here is someone called Sir Humphrey Davy, and I've included him because he was the first one to start giving lectures to the public about science. Before then, science wasn't called science, it was called philosophy. People used to think that science was dealt with by thinking about things. And so lots of old men with cups of port and a pipe would sit in the drawing room and go, "Oh boy, I think I've thought about particles." And the other one would go, "Yes, John, I agree, particles, yes." And that's how science was done. Humphrey Davy was the first one that said, well, actually, why are we keeping this to ourselves? Why aren't we letting everyone know what we're doing, and maybe we'll get some ideas back? So Humphrey Davy started giving lectures from the Royal Institute in London. Now, he decided he was going to do the 1827 one, but he became ill. He had a stroke in that year. So instead of him doing the first one was done by someone called John Millington. I've looked on the internet, there's no pictures of John Millington, so you have to do with Humphrey Davy. Now, they decided that the Christmas lectures was going to be a one-off set of lectures specially designed for children. And that every Christmas they would do something for children at the Royal Institute. Now that's happened every year since, except for during the Second World War, the building was damaged in the Blitz and they didn't do it for 2 years. So every year they've done some, and there have been some incredible speakers. Richard Attenborough has done one.
Dr. Grant, my dear Dr. Sattler, welcome to Jurassic Park.
David Attenborough
has done one. It's called Carl Sagan has done one. Most of the big scientists of our time at some point have done a lecture on this. So I just want to point out a couple of ones. The main guy that's made this really popular and famous is this guy, it's Michael Faraday. He was actually Humphrey Davy, the guy before's assistant to start off with. He was his lab technician. He was there to help prepare everything, and while he was there, he got to work with electromagnets. And he designed what's become generators and our way of generating electricity for the masses. Now, he took this on and really excelled at the Christmas lectures. He made it so that it was a really popular thing. He did a series of 30 of them by the end of the topic. And he kept on going right into his 60s. So this guy's really important. Now, I kind of want to point out this year, you might recognise the lady that's doing this year, in that you've kind of had a taster of what she's going to talk about at the Christmas lectures, because at our prize giving, she gave a talk about who I am, and it's about where we come from, and ancestrally looking back at the human species. So her lectures this year are going to be about that. And if you want to, if you enjoy this, you can catch them on BBC4, and I looked on the website, it doesn't say exactly when, but it is there. BBC4, you'll be able to catch the lectures. If you go on the internet, you can actually see all of the old lectures going all the way back to 1973. So you can have a look and listen to, I quite fancy that one, I'll have a look at that one. So they're there and they have been done every year. So without further ado, my lovely janitor here, Mr. Kippax, is going to show you a little bit about fireworks and metals, and I'm going to stand back and set fire.
Set fire to you. Now, one of the things, I am a chemist, I love making explosions. In fact, one of the reasons I became a chemistry teacher was to set fire to more things, because we have more chemicals to play with. We do some teaching on the side, but the biggest thing I like doing is setting fire to things and wondering why, looking at the colours. Those of you who were here for the bonfire night, put your hands up. Excellent. Now, what happens there is that the Chinese, they came up with the idea of fireworks. They set these things off, they exploded. And the colours in the sky that you see are all down to the metals that you see in the periodic table. We're going to try and reconstruct some of the colours that you see in fireworks. A little bit of background. If you put a metal into a Bunsen flame, you get a colour. Depending on the metal, you get a different colour. So here are some pictures of Bunsen burner flames with different metals actually put into them. And they give off a lovely, different glow. So the spectacular fireworks and the colours you see in the sky are simply metals being blown up into the atmosphere and then explode, and beautiful colours and sparks that we see that may well make us go, wow, now what's my next one today? That was not blank. There we go. It's there. Now, fireworks, we believe, were around the Chinese about the 7th century, is it? That's one time, about 1,300 years that they've been doing it. Less amount of time in our country. We've got a problem with that. They are made from chemical salts and gunpowder. So, what we asked, we went to the head and said, please can we have some gunpowder? Do you know what he said? No. So, unfortunately, we do not have gunpowder to play with. But what we can do is put on an explanation. This is...
Well, we're not enjoying it.
We're not enjoying it. Hang on.
My bit is very smooth.
It was very smooth. Mine is not very smooth. That's what we want. There we go. Now, what we can do is take some of these metals. We can put them into flammable liquid. We can spray them into a flame. The green menace over here is going to be my wonderful assistant. What we're going to do is we're going to set fire to a split. I'm going to shoot him. It's been a pleasure. 3.5 years I've been waiting for the pleasure to shoot flammable liquid at my boss. I'm going to do that. What you need to do is, as I shoot these, we're looking for some of these colours and see if we can identify the particular metal that I have sprayed at Mr. Harding. It is just a pleasure to be able to do this today. And, if you've got anything you want to say to Mr. Harding this last moment,
Alright, what was that?
What I want you to do, look very carefully on your ship flame in your direction and see if you can see any different colour. Here you go. That's better. What metal do we think? Right, that is calcium. If I dissolve calcium into flammable liquid and spray, I get a lovely colour. Some fireworks, particularly sparklers and other things like that, have a little bit more calcium in them. Right, number 2. So carefully, this one may be a little bit different. You nervous yet? No? Alright, well, I'll move the...
I trust you.
You trust me? Silly man. Right.
Do
I have to aim at the flame? It's not orange again. Try this one. That one was fairly fancy. Sonia? Try again. Right, one more time. What did you say? This one. Ready? What did you say? That was barium. Now I'm going to try a couple more. I really think your eyes on this one. This may work. Those of you who can talk by me should know what my favourite element is. What is it? Potassium. Good. So this might look like potassium, but it doesn't dissolve very well. It's a little bit scary. Potassium.
Yeah, 6 purple is right in the flame. Look, you have to look carefully, the purple is there. Right by the split.
There it is.
A little bit of
The problem is ethanol is yellow.
There it is. If you look right
we're trying to get across, I suppose, today is about chemical reactions. And for things to react, we've got to have certain things happen. Now, in terms of this next experiment, we're going to talk about something called collision theory. And the idea is this, is if I take two chemicals, in order for them to react, they have to hit each other. And I can change conditions to make that happen at different times. So, what I'm going to do, I'm going to do an experiment, I'm going to line up with you helping me. Hang on, put your hands down. And I'm going to set up the conditions where the particles inside a liquid are going to hit at different times. And we will get a chemical reaction occur. Now, who has been listening in my lessons? Wait, put your hands down. The question is, how can I tell a reaction has taken place? What are some of the signs for a reaction having taken place? Yes?
It doesn't go backwards. It doesn't go backwards.
I've got to form a new substance. New substance can be a different colour. So I'm going to look for a colour change. Sometimes I get heat. The chemical reaction you saw here gave me heat. Sometimes we get bubbles. Sometimes that is liquid and gas before. Sometimes it's not so obvious, but on this particular one it is. So, how to choose H1 Jack? Hayden, I was going to head to Sam, Harry, Xanthi, Matilda, Tallulah, and Camilla. Sorry, you get there in a minute. Brain, focus, come on. Right. Goggles need to be on, and you need to wear a pair of gloves. Okay, now, sorry, Harry. In order for this to work, I think a little bit closer, so we're kind of like evenly spread. And when I say go, all I want you to do is to pour that into that. So the measuring cylinder gets poured into the beaker. Then, so I pour it in, I would then put the measuring cylinder down, and then I'd stand with the beaker in front so everyone can see the liquid. So I probably would hold it like that. Okay, are we ready? Get ready to pour. Ready, steady, pour. Now we did try this morning and it worked perfect. So put the beakers down and the down, put the beakers out so everyone can see them. So right now the particles inside the liquid are mixing around. Some are colliding, some aren't. And watch them very carefully. Now I can't remember which order I did it. Either Matilda or Sam, whichever one goes first, and it'll be an obvious change. When it goes, then we can start looking down the line. So we're waiting for enough of the particles to have collided in order to make it change. Now we did this morning, and it took 35 seconds for the first one to go. However, that was a little bit warmer because I've just bought a kettle that made the solution. So I'm expecting this to take a little bit. Why do you reckon it takes longer? One's gone. One's gone. Now watch. Right, so we're going to watch the second one. So, there we go. So,
I'm going to die.
Look at number 3. So, we're on to the next one. So, I'll tell you how I altered the conditions in a second. We're waiting for Xanthi. Xanthi's always Xanthi never does anything on time, including this experiment.
I think it needs some magic words.
Well, I'm pleased, at least 3 of them, because this could have been completely disastrous. And so, what we actually turn to, Sam, it will go eventually, is we turn to that.
It looks like a vinegar.
So, yeah, what I think has happened is if I don't get enough particles to collide, and what I've actually done on each of these is I've added an amount of water to each one. So this one, we talked about 100% solution. 100% means I had complete slowly it's going. So I start with 100% solution. That means I've got 100% pure, and in this case I use hydrogen peroxide. Hydrogen peroxide 100% needs to collide. Now on this one here, I had 50% hydrogen peroxide, 50% water. So I've got half the particles inside this one. You just give me a stir.
Yeah, I'm just going to try and convince the particles.
That's the world.
It does now. We can always cheat a little bit.
Yeah, I think.
Shall we cheat a little bit? See if it captures. So by increasing the amount, I get the particles to line. Okay, so then I have the focus back on there, please. So collision theories, for reactions to take place, they must collide. Thank you very much. And for my unfortunately, this next one requires me to act. Good luck.
We've all seen, well, we've certainly all heard of the wonder of water to wine. We've all heard the first miracle. As scientists, we're obviously concerned about that ability to do that. We wanted to replicate it, see if we can do the same trick. Can we turn water into wine? Can we turn water into wine? Who believes that it's possible? Good, I like faith in science. That's good. So what I've got is just an ordinary bottle of Port Regis tap water. Yes?
Port Regis wine?
Port Regis tap water.
What kind of establishment would make wine? Port Regis wine?
Well, you haven't tasted it. It's actually Port Regis water. I'm going to turn it into Port Regis wine. What do I do? I think I should cross your fingers. Thank you. Right. Port Regis wine. It is an excellent vintage. Have some Port Regis wine.
That's no good, is it? At my dinner party, I'm not serving water to my guests.
It's not water, it's white wine.
Oh, white wine.
It's white wine.
That's what children drink in France.
What do you like?
Clearly, I need some red wine for my more established guests.
Red wine. Do you think I can do red wine? Pardon? Red wine, sir. Red wine. Red wine. Red.
Red wine.
Red wine.
Hang on.
Red wine.
I know this Port Regis wine, but look, this looks off. Would you drink this? Look at the state of that.
It's rosé. Come on, I know, it's rosé. It's rosé.
Hang on. Still white wine inside. Calm down. You see those? It's not just pouring, it's still clear.
Thank you. Can I have my wine back? I mean water.
Right, let's try again.
Red wine. Did you say red?
Red.
Well, I've got some excellent
Not this
red wine.
rosé.
Red wine.
Red wine.
Yeah, it's red. I've just turned it into red. Red wine.
Well, that's terrible.
Well,
That's just not working. milk for my...
Milk.
Yes, please.
Milk. I haven't got a cow.
Well, you miracle worker, turn the wine into milk, please. Yes, the wine, my wine into milk, please.
Milk. It didn't work. No.
Do you know, yesterday we tried all of this. It was magnificent. Magnificent.
Hang on. Milk. I'm not doing anything, that's it.
Wow! Look at that!
It's magic.
Magic.
In all seriousness, the idea again behind this is when you pour, thank you, when you pour two different chemicals together, if we get a reaction, sometimes the reaction can be a different colour. In this one, we were trying to subtly leave a little bit of what's something called phenol fading at the bottom. This will work quite well.
Just because you don't like it.
On this particular one, we were trying to leave something called universal indicator. Well done to those that spotted the subtle wine bottle swap. We did swap the chemicals over from, this is an alkaline, which turns purple. This is an acid, which turns red. So we changed subtly the different reagents used. On this one, we actually make a white powder. And so it looks like milk. In fact, milk is little droplets of fat inside water, which doesn't quite dissolve. So it's the same principle. So by having that white powder, you can then create something that looks similar to milk. So each time we do a reaction, we're looking for the products we come back with, and we're looking for changes that's happened there. Ready for number 4? So, my next one, continuing what I would like to talk about in terms of reactions. Sometimes the reactions that we get create heat that happens so fast that it actually explodes. Explosion is just heat produced and released rapidly. So in order to do this, I'm going to explore the reaction of simple burning and combustion. So I'm going to start off with what is burning. Can anyone describe what burning is? As a principle, yes?
Combustion.
Well, it is combustion, but what actually happens inside something that combusts?
That's a chemical reaction.
Yeah, it is a chemical reaction. Do you know that? It will produce heat. You know? It doesn't gain weight because it fades away. No. I'm not going to go with that.
Is there friction?
Not to do friction, no.
Well, when it gets hotter, does it change colour?
It sometimes gives off a colour, so combustion usually gives a flame of some kind. We missed the point. What thing do I need for things to burn?
Oxygen.
If you put your hand up, they might ask you, Sam. Well done, I don't know how you got that, congratulations. Oxygen. So a combustion reaction is putting something with oxygen and giving it enough energy to start colliding. Usually, the thing I add in order to get them colliding is a flame. So I'm going to do a little reaction where I'm going to take a fuel. The fuel I'm going to use is something called methane. You've probably all heard of methane because it does smell and I produce a lot of it after baked beans. The formula though for methane is this. A methane molecule has got 1 carbon and 4 hydrogen atoms joined together. The formula for it is CH4. And it's slightly ironic that Mrs. Taylor teaches in the room that's named after methane. The other chemical we're going to react is oxygen. If you see the oxygen here, we get 2 oxygen molecules together. We call it O2. So in order to get this to happen, I put those 2 together and then I add a flame. And the flame will start those particles colliding. Now, to make this more interesting, I've changed the different solutions, mixtures of both. In each bottle, I've put a combination of methane and oxygen. This one on it says 100% methane. It's got 0 oxygen in it. Now, when I put a flame in this, technically what should happen? It should go out. However, it won't, because I can't exclude oxygen from everywhere, because where is there oxygen that I can't get rid of without dying?
It's your
Put your hand up, then I can ask you this building, air. I can't get rid of the oxygen completely because this air is in here. So I've done this before, and what I used to do was I used to open up the bottle, put a flame in, and then it explode. And there's a few issues with that. It tends to melt, and then it tends to shoot at you at high speed. I've been experimenting, I've been waiting, and I've come up with this, I think, slightly ingenious way of doing it. I'm going to fill up these. I have filled up these. I'm going to put a cork in, and I'm going to blow this out into bubble mixture, and then I will get bubbles filled with this gas. Simple, yes? I will then set fire to that, so if we get an explosion, the only thing that's going to shoot at you is bubble mix. Should be safe. Should be. Now, I'm going to start with my 100% methane, and I'm going to expect this to react to the air around it. And probably, like methane coming out of the Bunsen burner, I will probably see a flame coming out the top. So let's give this one a go. Yeah, I think we'll have some lights on for this one. Here. Chris, can you just hold that? Okay.
It does actually smell like you have black beans as well.
So, first one, just in case, I'm going to put this on. Good practice. This one should make a bang, but I can't guarantee that I've got to make sure it's exactly right. Can you put your hands over your ears? I'm not expecting an explosion for this one, but it's best to be safe. So I'll take a flame, we'll go to the bubbles, and I put it in like so. Okay?
Bang.
That is exactly what was expected. That was exactly what we were expecting. There was no oxygen mixed in, and so there was no collisions that could happen unless it reacted with the air around it. Right, this one I'm going to put 25% oxygen, 75% methane. So now I've got the potential of collisions happening quicker. I should get a little bang. Little bang.
Right, put your hands over your ears, please.
Okay, thank you. Okay, so, little bang. Oh, no, not yet. Okay, but now I get on to 50% methane, 50% oxygen, and I'm now getting to a ratio that should become explosive when I'm out. I'm not anticipating this one to be the loudest one, but I am expecting this to at least pop.
So when people get it, it's going to the top. They're on
Why can't I put my hands over ears? Hands over ears, this one should make it, man. Please. Okay, ready? Oh. Okay. This one doesn't work, I will officially cross it. You will see a grown man cry on stage if this does not work. and it was amazing. It was really, really cool. So if between today, yesterday, and that okay. Hands over ears. Got out.
Wow.
Right, come on. This time. Ready?